Hello everyone. Here I would like to introduce you how to use the web interface to build input files for RMG. From the GitHub, you can search the RMG DFG, then they will pop up three projects. The first one is our main code, the ab initio code for the electronic structure, and then this one is for the post-processing of our data. This one is an interface to generate input files for RMG. If you click this, you see this is a file if you are now interested in, but here in the right panel, there's a link. This will link to a Streamlit. This is a cloud to hold our interface. If you click this, you will see a little bit slow to upload. This is web interface to generate the RMG input files. For example, here we have two clicks. One is for the RMG base code. This will be the way function will be described as delocalized in real space. Another one is use the localized orbital module. This will optimize numerically the localized orbitals near the item. If you click this, they will have different output for the different branch of the code. Let's focus on the RMG base code. First, you need to have your original input file, either a CAF or XYZ or VASP or QE. You can browse the file here or just drag the file and put here. For example, if you can do this, let me find one. I have a bunch of it, but for example, this one you can have XYZ files. They will upload the file. This is a file name you uploaded, and here in this way you can set up the lattice informations. For example, because this is a molecule, you don't have lattice informations. You can here you set up, or you can just use all examples. Here we have, for example, if you click use the example to see how can we use. For example, if you click CAF, this will have a iron arsenide CAF file as an example. If you click XYZ, we have a carbon-60 for the XYZ files, also the VASP. This is a BN, boron nitride. We also have a QE for the example. This is for the diamond. And let's for example use this XYZ files. You can view the atomic structures here. This is just carbon-60, a buckyball. You can also make a supercell. For example, this is one buckyball, but you can make supercell. You say I want to double in this direction. You type to this way, your structure will be doubled. Or you can do another way, 212. This will be in the Z direction. This will be 4. Definitely, you can do any kind of repeat over your unit cells. Let's see still one by one. And this will be carbon-60. If you don't need to view the structure, you know the structure, you don't need to do that. And then here is the basic options. If you click this, they will give you, for example, here how to choose the real space grid. This grid spacing in Bohr. For example, for this one, carbon-60, the 0.38 should be good enough. You can either increase or decrease. You can click this. This will be increase. Oh, this need to increase a lot. You see, when you increase, this number will be decreased because there's a number of grid. When you decrease, for example, you decrease a lot, they can just increase. But here I just say, every grid point will be times 8. This will be good for the real space to do the multi-grid. here is the, usually in the real space, this will be the grid for the wave functions. Here for the RHO, for the charge density and the potentials, you can have a fine gradient, then the wave function usually we use double or triple or 4 times. Here they give you the final grid spacing. Here I think in Angstrom. After set up this, you can also set up the suit potentials. Suit potentials in our code, we have built-in suit potentials. One is ONCV. This is from the Hammond's suit potential. This is normal conserving. Another one is the GBRV. This set is ultra-soft. All these suit potentials can be downloaded from the internet, but we just include it in our code. Or you can also say, if you have your own files, you can click here. Then they will ask you, for example, your suit potential file directory. You can give a directory, also give a name. For example, here for the carbon, what is the name of your suit potential is. You can specify it, but we only support the UPF or XML format. We don't support other format. Here's some flag to write suit potential plot. This means you have suit potential, you want to see how the local potential looks like, how the projector looks like. You can do this. And also here, if you click this, you can tune the localization of the suit potentials. For example, the projectors for a very small system, we find it's best to use a non-local projector localization. This is like non-local projector we call localization, or the local potential localization. If you click this means they are local. If you unclick it, this means they are they are delocalized. This will be very close to the plane wave code, but for very large system, it's better to keep this checked. This means your projector, non-local projector will be localized, and if you have a question mark here, you can put your cursor here. You can see false will be non-local projector will spread in whole space, similar to plane wave code. This one's true. If you click it, this will be localized, but then definitely you can just unclick it. And if you click it, then you can see this one. You can define the maximum radius of the non-local projectors and your max and minimum radius. I think this may be a misprint. Here is the local for the Q function. If you have ultra-soft potential, you have Q function for this. After you set the potential setup, here also have a key point setup, and by default you will have a gun point. This means your whole point and the whole wave function will be real. This will be a fast. But if your system is small, you say I need a key point. You can either click the use mesh. Then they will say what kind of mesh you want. For example, you can say the 3x3x3, and also like key shift. This you including gun point or not. This key point distribution, we have a lot of key point. When do the parallelization, you want to how many processors parallel over the key point. Here you can choose. For definitely this cannot be larger than the total number of key point, but you can choose. You can also say I have a list of the key point, and you just put here all the list. But then this will be the 3 vectors for the key point, and then you have the weight for the key point. Another one is if you want to calculate band structures, usually when we calculate band structures, we want to use key point along a special lines. Here you can do that. For example, here this is the gun point, This will be an X point. You say from gun point to X point, this will have 20 points here. And after you calculate this, you will have a band structure over this. Definitely you can have more. For example, here you want to say, I want to do the 2.5 to 2.5, another 0.0, and another, this will be K point, something like that. Then this need to be the control inter for the to get the effect. So this means your K point will, like from gamma to X will have 20 point, from X to K will have another 20 point. You can also use the list. This one may not, should works, but why they didn't show anything. Anyway, here maybe not the correct one. Just band structure use special lines. Then another one will be the control option. Control option, like for the start, usually you just choose LCO start, but sometimes you cannot get a conversion in one job. You need to restart from a file. You can click this, you generate an input file for your restart. Other start, like a random start, this for the test, but not very useful. And this fireball start is for the, and the Gaussian start, this for the localized orbitals. I will not discuss here. For the calculation mode, you can either choose the quench electrons only. This means you don't relax structures. You only do the self-consistent for the fixed structures. Or you can click here, do relax structures, relax the atomic structure. You can also do the molecular dynamics, choose a different mode. And definitely you can do the band structure only too. So diagonalization, these libraries, if you choose automatic, they will determine either LAPACK or SkyLAPACK. If you don't have a GPU, if you have GPU, they can use CoolSolver or RockSolver. This is not very efficient, but you can choose different diagonalization libraries. Also, Kongxiang solver. For a small system, Davidson will give us a very fast, very accurate results, but the multigrade will be a little slower. But for large system, the multigrade will be advantage than the Davidson. For example, if you have 1,000 items, Davidson could be very slow, but the multigrade will be reasonably fast. This is a basic control. For sure, we have more controls. If you want, you can say, click this. You have more, like how do you control the Davidson diagonalization procedures? How do you do the Poisson solver? And also how do you do the relaxation and Fermi-Dirac distribution? Everything different. Just more options if you click this. Another is like exchange correlation potentials. Usually we just determine from pseudopotentials. If you choose Alt XC, this means whenever you choose pseudopotentials and the pseudopotential, what kind of exchange correlation potential you use, they will use this. Definitely you can also choose all different by hand. For example, you can use, if you want to include in Van der Waals DF corrections, or the hybrid like PB0, PB-SOL, and the HSE or whatever you want to choose different. We also have empirical Van der Waals corrections like Grimy D2, D3, and also called DFT D2. The different empirical one also have LD plus U. If you say I want, but we only have one mode, if you click this, simple, and then you need to be Hubbard U for the species. You need to give this one the Hubbard, give a Hubbard U for that. Okay, I think this LD plus U. Also the spin. If you do a spin polarization calculations, here you just do the spin. And then in the initial, you need to say like what kind of like this may be not a very good one, but for the spin, let me, yeah, just need to like initial spin is how much percent. For example, you can say 0.2 something like that. This means that you will have like 20% more for the spin up than the 20% less for the spin down. This is basic options. Another one is commonly used options. You can check this box to get more. This like when you have this one, you have like SCF steps, all this controlled convergency stuff. Also the mixing options. You can use Broyden, pulley, or different mixing scheme. We also build a QMC pack interface. Here, if you click this will write out the file name for the AF QMC for the RMG. This for the one QMC pack needed. Also, they will have a Cholesky factorization for the exact exchange correlation. Definitely, we need to calculate this. This factor should be fine. Number of bands for QMC pack. This one, in fact, the default value, this means when you use 0, this will use the number of states as your number band. You can change to the different numbers. This file path, this usually I would not suggest you to change. They will automatically build. And okay, this. We also have a lot of other options in the code. When you check this box, we call the MISC options. They all have a bunch of it. If you want Go, they have a lot of like, depending on like for example this one like Kongshan FD order. This means usually we use 8. You can use 10 or 12. For more accurate calculations. Also a lot of different parameters to control, to tune the performance on different architecture, different computers. Okay, I think this most is this. And okay, if you set up all this stuff, I see this one. I think that usually we don't want this. This will have a very, very long output. And you can click show the generated RMG file. This will looks like what it looks like you generated for the input file for the RMG. And for example, this one I think that usually we don't need something. This one, if we don't check, they will not show. They will be much shorter. And another one is pseudo potential. Yeah, if you don't tune this, they will just don't show anything there. So it will be easy. It will be shorter. You can see here they generated. They have the base wave function grade and calculation mode. Why I choose band structure only here? I forgot. But anyway, calculation mode. Show the potentials, key points. Oh yeah, I don't know why I click this one. I just show you different options. But anyway, when you change this, you can see that originally we have a calculation the band structure. Now the calculation mode equal to quench electrons. All this kind of stuff. And also pseudo potentials. In fact, for pseudo potentials, if you don't choose pseudo potentials, they will show different. Let me see the pseudo potentials. Let's unclick this. For example, if you just use ONCV, the internal pseudo potential, in the output, in the input file, you will see where the pseudo potential come. Yeah, here's pseudo potential. Just say use internal pseudo potential type is NC accuracy. This is a non-conserving. It's an accurate one. Like I I think this from the we just use this as for this one kind of ONCV shooter potentials. Okay, I think that's it. And here the last is the atomic positions. They just like coordinate different types. Okay, I hope you can learn something from here. Thank you very much.